the interesting part is in retrospective, you always try to spin a story around it. But if you make these decisions back then, it's of course it's to some extent, it's not a random decision, right? But it's like very much influenced by kind of who you know and by what opportunities you have. So the story I kind of tell you now might not really reflect of how I got into it.
A quick word from our sponsor for this video, Rora. Rora helps top AI researchers and professionals negotiate their pay as a transition from academia into industry. Moving into tech is a huge transition for many PhDs and postdocs. The pay is much more significant and terms of employment are often quite different. Rora has helped over 1,000 STEM professionals negotiate more than $10 million in additional earnings from companies like DeepMind, OpenAI, Google Brain, and advocate for better roles, more alignment with their managers, and more flexible work. Rora recently released their 2023 AI Researcher Compensation Guide, which I'll link into the show notes. Click the sponsor links to get discounts and support this podcast. All right. So hello and welcome everyone to whoever's listening to this particular podcast. I have with me on my show today Dr. David Stutz. David is a research scientist at DeepMind working on building robust and safe deep learning models. Prior to joining DeepMind, he was a PhD student at Max Planck Institute of Informatics. And apart from that, he also maintains a fantastic blog on various topics related to machine learning and graduate life, which I think is really insightful for young researchers out there. So I'll leave a link to that in the show notes. But we'll be talking more about his past research work, current work, and his interests and his insights onto the graduate and research life. So it's good to have you on the show, David. Welcome to the podcast.
Yeah, thanks for having me. That was a very flattering introduction.
So, I mean, a lot of people already know you and from your blog posts and lots of other things that you have posted. But can you explain to us, like, what was your interest point in AI? Like, how did you personally get intrigued about the idea of AI?
Yeah, that's a good question. I think it was to a large extent incidental in the sense that when I started studying, so I already knew how to program and I knew the basics of computer science before starting. And then in the first couple of years, I got really excited about like mathematics because mathematics was kind of the challenging part of my undergrad for me. And so I started kind of delving more and more into mathematics. And on a computer science side, we had an excellent computer vision group where I did my undergrad. And they started offering computer vision and machine learning lectures. And I kind of found them to be on the more difficult side for computer scientists. A lot of math involved. I had a lot of kind of numerical analysis and numerical linear algebra lectures on the side. And so I found it really interesting. And on another side, it was also like incidental in the sense that, friends and people I studied with at that point that I did kind of exercises and homework with also got interested in that. So it was kind of, I think, a combination of being excited about kind of the math side of things and seeing how kind of all this kind of fancy mathematics can be applied to kind of really relevant problems. And at the same time, having like people around me that kind of encouraged me to, let's take this lecture together and see how it's going. And then it spiraled from there, right? Once you start with a couple of lectures, there are more advanced lectures, you get to know the professor and so on. You start doing your bachelor thesis and your master thesis there and so on. So I think that's how it started. Of course, there are a lot of things that I find personally interesting about machine learning in general. But I think, I mean, if I would have worked on, let's say, networking, I also would find a lot of things in networking interesting. So I think it's a combination of interest and being pushed by your environment to kind of specific topics and having the availability of kind of really good lectures and smart people and so on.
Yeah. And I would assume, like, since you were on the majority of the side, people who might feel intimidated by the mathematics and the things that goes behind building a machine learning model. So I would assume that it was the application side of it, like most of the people, how they use computer vision algorithms and make fantastic predictions or something that would have been the driving force. Like you said, like if you would have been into networking, you would also stay with that. But like something that AI or maybe machine learning models do more than just applying it to certain set of problem sets that would have intrigued you more.
Yeah, exactly. I think so. I think initially what I really liked is, so I did a mathematics minor, and I also did some additional lectures on mathematics in my first 2 years. And in the first really kind of tough lectures I had, so in my undergrad, you could choose like a minor. You could do like computer science with minor mathematics or minor business or something. And I chose minor mathematics. Not a lot of people did that. The main reason was because the lectures you had to take in this minor, these weren't like lectures for computer scientists, yeah, right? So you had basically you took like all people that chose this minor and you just threw them into like the real mathematics lectures, and it wasn't always really designed very well. So sometimes you like the people studying mathematics had like lectures like 1 to 4, but you were thrown into like 2 and 4, and kind of they assumed that you would learn like the lectures in between by yourself. And the first one we were thrown into was numerical analysis. So it's basically numerical linear algebra and calculus. So kind of how do you fit polynomials? How do you kind of do your QR decomposition and all that stuff, right? So from a mathematics standpoint, this was kind of the really applied stuff. But of course, coming from computer science, you didn't just like do it and implement it, right? So you had to go through the proofs and you have to kind of understand the mathematics, and then you implemented it in kind of C back then and so on. And I think that was the entry point in thinking about like how nice you can apply these kind of mathematical principles to fitting problems, right? I mean, in numerical linear algebra, these are a lot of fitting problems like QR decomposition, SV decomposition, and so on. These are like, in a sense, these are all kind of tools that in machine learning we use nearly every day, right? So it was a very natural thing to then say, okay, yeah, we have machine learning lectures and computer vision lectures on the computer science side. And yeah, this looks like these people are actually applying all these tools. And yeah, as I said, then there was also this kind of incidental thing of having a good friend that kind of did the mathematics minor with me and kind of also went in the same direction. And so it was like a lot of good arguments for going that direction. And then we had very good lectures, and the group or the professor doing the lectures was really open to having kind of bachelor students join and having your kind of doing your thesis with him and so on. And that's how it started. But yeah, I think it's for me, it's really kind of seeing kind of going from the proof and then seeing kind of, okay, now you prove that this decomposition works, and now like for this computer vision problem, you can actually break it down to that, right? Yeah. And I found that very interesting. And then of course, it kind of spiraled from there a bit. If you think about all the basic machine learning things, these are all, in a sense, it's a combination of, in my mind, it's a combination of statistics and numerical kind of analysis or numerical kind of mathematics. And I really enjoyed that back then because I also found it challenging compared to a lot of the other lectures that we had to take or that we could optionally take. And yeah.
Yeah. I mean, I'll just second that on based on few of the thoughts that I had, like, because when I got started into machine learning, like you said, like I was most intimidated by the mathematics and the, like for you, like you said, like you had to work on proofs and everything, but that was the thing that I would consider as a con for me, like as in like, okay. I like machine learning, but I might have to deal with that. And it's completely flipped now. Like nowadays when I work with research, I think I'm working on like how do regression models have like an inherent bias in deep learning models, and for that I have to dig a deep down a lot of mathematics, like what exactly is a regression, what exactly weights, and like how do the back propagation happens, and how it affects the overall regression model on continuous variables versus discrete. And nowadays like the coins have flipped. Like I like that part more than just training a model. And when I got started into PhD, I just thought, oh, this is something what I'm doing. I'll be implementing code, writing codes in PyTorch, TensorFlow, and this is how my PhD going to be. And nowadays like training models is just like one part of what you do, but it's like what happens before that and after that that really intrigues. So yeah,
I think it's a good perspective realizing that, and I totally feel with you. My experience is also that, so the majority of people, for example, that I took these lectures with, most of them of course came from the computer science part. They were interested in computer vision and machine learning, but they didn't have the mathematics background. So for them, definitely the mathematics part was the difficulty, right? Because for me, it was kind of a bit the other way around. I was depending on how you see it, right? I was forced to, or I was fortunate to really go through like a lot of these decompositions and kind of fitting and regression and so on in kind of very much mathematical detail to the end that you kind of prove things and so on. So for me, it was kind of sitting in a machine learning lecture and saying, yeah, you can see that as kind of an eigenvalue decomposition, and then you just get like your vectors here and there, and that's how it goes. So for me, that was very natural because I spent like 1 or 2 semesters kind of digging into that. But I can see that for others, that's kind of probably the most difficult part of getting into it. And another thing is, of course, that so when I started the first lectures on computer vision and machine learning, it was in 2013. So there was already AlexNet around, but kind of deep learning hasn't really penetrated the whole of computer vision back then. So all of the machine learning was really, there wasn't a lot of deep learning, right? So you learn about perceptrons and multi-layer perceptrons, but this was kind of, back then, kind of the boring part, right? It was much more excited to get into like all these kind of random forests were very interesting. Also support vector machines were like super big, right? And support vector machines inherent, like you can have, there are lectures or there are kind of researchers that just spend their time on kind of proving how these support vector machines work in specific spaces and so on, right? So there's a lot of mathematics behind there. And I can very easily see that for a lot of people, this is kind of a deterrent to some extent.
Yeah.
But on the positive side, I think that's great about that nowadays you have a lot of these tools very readily available, right? Through not only kind of TensorFlow and PyTorch and so on, but also like scikit-learn and so on. So you can use them before you actually understand them. And I think that's a good entry point, because if people use them, they get curious, right? You want to know how it works. Whereas the other way around, first learning how it works, first going through the math, and then occasionally seeing how it kind of works in practice is, of course, the way longer journey, right?
Yeah. And this is what I would say like is like the iceberg of getting into machine learning, right? So this is like the surface point of barely scratching what machine learning looks like. So can you tell, like we talked about how you got interested in AI, but nowadays you're working on robust and safe deep learning model, means like how deep models generalize to external data sets and how exactly the idea of robustness and generalization affects deep learning models. So how did you go from that journey of like, okay, I'm interested about these things, to building like a full PhD thesis that you can claim you are an expert on? So what was that journey like?
Yeah, I mean, I can go a bit through that journey, but the interesting part is in retrospective, you always try to spin a story around it. But if you make these decisions back then, it's of course it's to some extent, it's not a random decision, right? But it's like very much influenced by kind of who you know and by what opportunities you have. So the story I kind of tell you now might not really reflect of how I got into it. Anyway, so this is how it started, right? This was during my undergrad. I took the first 2 lectures, and I did my bachelor thesis on computer vision back then. This was on image segmentation. So not a lot of machine learning. There were, of course, methods that used kind of graphical models for image segmentation were very popular back then. So there was kind of some machine learning, but not the deep learning part that kind of consumed a lot of machine learning nowadays. And I really enjoyed that. I kind of got to do a lot of programming in C++, try out kind of a lot of different data sets, get to know like how the thinking in computer vision and machine learning works, like how you evaluate and so on. And I think then the first pivotal point in kind of getting me to a PhD was that my advisor back then suggested submitting the results of my bachelor thesis to a German conference. So there's a German conference on pattern recognition, GCPR. And GCPR back then had a, I think it was called a young researcher forum or something like that. So a specific track of the conference. So this is not a big conference, right? So this is not like CVPR or something. Back then it was kind of a couple of hundred people most, and then maybe like papers in the number of like tens instead of like hundreds. But they had this specific track for like undergrads and master students to submit basically their thesis work. I was, of course, super excited to do this. And this year, the conference also happened to be in Aachen, where I studied at that time. So I wrote like today you would call it a short paper, essentially. I wrote a short paper based on my bachelor thesis. I got to go to the conference. First time meeting. Really, we had great keynote speakers back then, and it was the first time that I actually was able to meet kind of a lot of the well-known researchers, at least in Germany, or to some extent also from Europe and the world. And I got to present my poster and so on. And this was kind of the first interaction with the academic world, I feel. And for me, it was like a very positive one. And I think that had a very big impact on that. Academia for me was always kind of a very natural way, a very natural kind of opportunity to pursue. So this is how I started. And then through the master's, it kind of converged to considering a PhD more and more. I did a couple of internships, most of them in computer vision, in machine learning. But I, for example, also did an internship at Microsoft that was purely software engineering based, essentially kind of web development. And yeah, it's not that kind of the Microsoft internship wasn't great, or it's not that I kind of didn't like industry. I always worked, or I mostly worked in industry throughout my studies to kind of finance my studies. And but the part that I found challenging and that I was excited about was kind of, okay, what research question can you work in? How can you get like your first real kind of paper? Can you kind of go to the next conference? And yeah, this is kind of how it converged for my master thesis. Then this was also to some extent luck. I ended up in Tübingen at the Max Planck Institute doing my master thesis there. And this is how I got to know the Max Planck Society as a whole. So the Max Planck Society is I think one of the biggest fundamental research organizations in Germany, and it has institutes everywhere. So you have like institutes for math and for physics and so on. And computer science essentially has a big one in Saarbrücken, where I did my PhD, and then it has one in Tübingen, which is for intelligent systems. So there, Bernhard Schölkopf, for example, is director there, right? And I did my master thesis there, and yeah, I really liked it. I liked the environment, a lot of international folks. Very open, lot of kind of really good researchers coming in to give talks and so on. And yeah, by that point, I think I intuitively already decided that I want to do that for a couple of years, and the natural choice is doing a PhD. And from there on, it was essentially just a question of where to do the PhD, how to do it, and so on. But maybe one interesting thing, I said earlier that there's a lot of coincidence going on. And one coincidence, for example, was that the lab I did my master thesis with in Tübingen, so this was Andreas Geiger, and he is famous for the Kitty data set for autonomous driving. And I signed up for the Kitty data set during my master's somehow. And at some point, he just sent around an email saying, yeah, I have PhD openings. And I was really hesitant at some point, but for a while. But then at some point, I just said, okay, maybe you just write back and you ask for a master thesis. And that's what I did. So it was like a very random event, right? And that's what I mean is that you can plan and you can kind of have the best intentions, but sometimes opportunities come or go. And sometimes people push you in specific directions, or like sometimes, I mean, you can start your undergrad with the intention to study X, but if there's no lectures on X, then eventually you end up doing something else, right? So again, there is this kind of element of surprise and coincidence, and then there is, of course, me being super interested in kind of machine learning and computer vision in general, and finding it very challenging, finding it challenging to like write good papers and publish. And that led me in the end to like want to pursue a PhD, I think.
Yeah, I appreciate the honesty that you have, and I think I can relate it a lot more. Is like if 10 years down the line, if somebody would ask me like, why did you get interested in medical part of AI? I mean, to be honest, like there are so many elements, like you said, and so many milestones that I can have like a general idea that I want to be a researcher in the field of AI. But like if someone were to ask me specifically, why did you work on, let's say like for my work, I'm working on brain age prediction. Like why did I work on that? It was purely because my professor was working on, and I got a chance chance to read about her work and be a part of her lab meetings, and then I got interested in that particular time. But if like that was not the goal that I joined that lab.
Yeah.
There were so many things that I could have been interested in AI. And so it's like if looking back, it definitely connects to a lot of dots, like you said. But yeah, most of the time, and I would say like majority, like more than a majority of people in AI would be eventually in that line. Like not a lot of people would have very sharp goal, like this is I want to do, and this, and like 10 years down the line they are precisely working on that topic.
Yeah, exactly. And I think it's a good perspective to have, because it also reduces the pressure a bit, right, of people starting their undergrad or masters and wanting to end up at a specific place, or wanting to do like a specific PhD or work on a specific topic, but in between a lot of stuff happens, and this is not negative, right? Being influenced by your surrounding, by what your professor is interested in, but what your peers are interested in, what's kind of currently on vogue in the research community. These are all good things in a sense, right? So you can have the best intentions to work on X, but you get sidetracked, right? I mean, I think generally, if I think about a lot of people I met in academia, it's like these are all kind of smart people. And most of them are generally interested in many topics, right? So it's not that I kind of woke up like 10 years ago and said, okay, I want to learn I want to work on Save AI or something. It's just that it's a challenging problem, and kind of coincidence happened to kind of push me there, and it could have gone to other topics, and I would have found them interesting, and I would sit here in the podcast and talk about other topics. And I think sometimes it's interesting and also a bit sobering to consider this kind of element of having a random world around you, people influencing you, and yeah, sometimes it can be your professor that really wants you to work on topic X, and sometimes it can be this random conversation over lunch. And afterwards you read this one paper, and that determines what you work on for a couple of years, right?
Yeah. But yeah, talking about the randomness, so I think you have been heavily focused on the idea of generalization and robustness in your PhD thesis, right? So I think like more like nowadays it's getting better, but I think there was a time that people were using these terms interchangeably, right? So having a robust model means it would be like a generalized model to external data sets. And this would typically mean like if you have a data set out of distribution, the model is like robust because it performs well on non-IID samples, and also it is generalized. So like nowadays, like can you describe the differences between these two? Like what do we mean by when we say building a robust deep learning model versus a generalized deep learning model?
Yeah, that's a good question. I mean, what you mentioned with the term robustness, it's of course in the literature we tend to overload terms, and then depending on which line of work you're looking at, it might mean something else. And coming from computer vision, I mean, this notion of robustness was around, right? People wanted to be robust in object detection. You want to be robust to occlusion or to weather changes. In learning, you want to be kind of some sort of robust to kind of feature changes or you handcrafted features that you had back then, and so on. The kind of robustness that I got very interested in, and maybe this is also a bit to the story of how I got into Save AI, is that when I started my PhD, there was a couple of years before, there were papers basically showing that you can fool classifiers, like usually deep neural networks, by these very slight perturbations, right? So you have an image of a dog and you add like a perturbation that you can barely see, like usually you can't see it at all. And the classifier says it's a cat or it's a car or whatnot. And these are called adversarial examples. So, and then very quickly, of course, people thought, okay, I mean, if these adversarial examples exist, this is of course like a risk. So we want to be robust against that. So this is kind of the type of robustness that I worked on. I prefer to call it like adversarial robustness, because it at least tells you a bit that there are like adversarial examples meant by that term. And yeah, in terms of generalization, I think the difference, you can say if you want to be adversarially robust, you can say you want to generalize to adversarial examples, right? So I don't think it's really coming down to if you write a paper, you need to distinguish somehow. So I think people started to distinguish a bit between kind of clean generalization, so generalization on like your test set, on like natural images, on images that haven't been manipulated, essentially. And then adversarial robustness on the other side as generalization performance on these adversarially perturbed images. So I think that's kind of a bit the distinction. And I think the only, or one part of why this distinction became interesting is because to date, so this is still the case, training models that are robust to adversarial examples usually comes at a cost in terms of clean performance. So if you want to be robust against adversarially manipulated images, you usually lose a bit of performance on kind of your test set, on your clean images. And from there, I think people got very accustomed to kind of this differentiation between robustness on the one hand and generalization on the other hand. But as you say, it's a fine line, and I think it's a very specific, let's say, a very specific use case in the literature of adversarial robustness. Outside, you would probably use it synonymously to some extent, right? You want to generalize to out of distribution, which could also mean you want to be robust to distribution shifts, right?
Yeah. And also in some of the experiments that you published, I think you also compared the idea of generalization and robustness. And you had some interesting findings that this trade-off is not necessarily present always. So can you talk more also about that? Like, because a lot of people, like you said, like even I had, like, to be honest, before I read that particular paper of yours, even I had that particular idea. And that was the assumption, because a similar problem that we have been working on is like we use this huge data set of images that are MRI images collected from different institutes. And there is this one very big institute called ADNI, where we have MRI images, and it's like the publicly standard image data set that people publish their work on for Alzheimer's. And when we tested our model on ADNI, it performs really bad. Like, I mean, it's not like bad by like a very small margin, it's like bad by a big margin.
Okay.
But when we
what did you train on? So you have like a different data set that you train on, I guess.
Yes. So it's similar. It's similarly like in terms of the dimensions and in terms of the modalities, it's still the same. We are still using MRI images, but just collected from a different institute. So they have like different imaging protocols, different pre-processing techniques. Like it's like just the difference of having a Philips scanner versus like a Siemens scanner. So that kind of differences. And when I tested on ADNI, which, I mean, to be honest, like ADNI is like, it's a study from more than 15 years. So I don't know if they changed scanners or something, but it comes from a group of institutes. But when we use transfer learning techniques where we fine-tune the model on the ADNI dataset, the performance is up to the standard. So it really helped me question that what's really going on. And when I use techniques like dropout, the performance increases. So that was the idea even I had, that yes, if I want to have a generalized model, if I can decrease the error, increase the error on test set from the clean data set in your terms, it will help. But yeah, I'll let you have the stage. Like, can you debunk that myth of this trade-off that exists?
There's an interesting perspective, because I mean, in the end, it's like a very inherent question to machine learning in general, right? You always, like, if you write it down in any textbook that you read on machine learning, like the first sentence, the first paragraph is, okay, we assume we have this data distribution PX or PXY if you want to include labels.
Yeah.
But in practice, of course, finding out what PX actually is. In your case, PX, you think that PX just entails MRI images of a specific body part, maybe. But there's so much more going on, because obviously, if you now go to a different institute, different hospital, you have, as you said, different processes, different, like maybe the patient lies in the scanner a bit differently. You have different protocols. You have different population, different patients, right? All of these shifts are relevant, and of course, you want to be robust to them, or in other literature, in other papers, you would probably call it, you want to transfer generalization to them, right? In terms of like the specific case that we usually looked at in terms of adversarial robustness, you can of course understand adversarial examples as a distribution shift, right? You can say, okay, we have the clean examples on the one hand, and now we add adversarial perturbations. Or it doesn't need to be adversarial. You can also say we just add noise or something. Then of course you have a new distribution that kind of like you could potentially even write down, if you just add Gaussian noise, you can write down how the distribution changes, but you have a distribution shift that you want to be robust against. Adversarial examples are of course special because it's kind of a worst case distribution shift, right? You look at the model and you try to figure out, okay, how do I need to change the distribution to really perform or to really fool the model on all the examples and so on. But yeah, I think the trade-off is present here and there. And in your case, it's nice to hear that you could overcome it. In robustness, that's, as I said, to date, still very difficult. And one interesting thing, so as you mentioned, one question that came up very early is whether this trade-off is kind of an inherent trade-off, and that it's kind of inherent in the problem. You can't get rid of it by kind of better methods or by, I don't know, right? So it's like you have a data set, and for this particular problem, there's an inherent trade-off that you can't overcome. And there was some evidence for that. There was also some evidence saying that it's not necessarily inherent. It's kind of a characteristic maybe of the learning method we have. And what we looked at is a specific method to obtain more robust models, which is essentially adversarial training. You can think about it as kind of data augmentation with adversarial examples, right? So during mini batch SGD, you kind of update, you kind of compute these adversarial examples and you train on them instead of kind of clean examples. And for adversarial training, you have like a very significant trade-off, right? I'm not sure if it's as significant as in your example, but you can really spot it, and it's too significant that you would say, yeah, that's kind of negligible for any use case. And if it would be an inherent trade-off, then any learning method you use would have this trade-off, right? And what we basically found, which I found very interesting, so from the beginning, I thought that I didn't like the idea of having this inherent trade-off, so I tried to kind of figure out ways around it. And what turned out to be the case in the end is that for adversarial training in specific, you just have higher sample complexity. If you want to be you want to perform well, and additionally you want to be robust against these adversarial examples, you just have higher sample complexity for your learning algorithm, which in this case was adversarial training, which means that if you would have infinite many examples that you can train on, then eventually you would overcome the trade-off, right? You would, of course, always, like, your clean performance would always be a bit worse than if you just train normally, right? But you can reach, let's say, the same clean performance as normal training, but you need maybe double or 10 times the examples. And I think nowadays, this is to some extent like an accepted hypothesis. There's been some follow-up work also confirming it. And there has been quite some success in terms of using kind of more data, using synthetic data, using kind of unlabeled data to overcome it to some extent. But I mean, you have to realize that at the same time, we also made progress on just the clean performance, right? So of course, we still lag behind the clean performance. That's kind of the definition of having higher sample complexity, right? But compared to where we were back then, you would definitely make progress. But this basically means that there might be a method out there that kind of overcomes the trade-off. But I'm not sure if it would be. I would expect that there would be other trade-offs involved there, right? You don't have a free lunch, so I wouldn't expect it there. And with machine learning in general moving to kind of bigger and bigger data sets and more data, I think overcoming it with more data to some extent is, or unlabeled data is kind of a realistic approach.
And is it like an oversimplification if I say that adversarial examples are the same as data augmentation techniques, or is there something more to creating adversarial examples that cannot be done using data augmentation?
So I like to call it more like an adversarial data augmentation, right? So I think so it depends a bit, right? So if your data augmentation is, let's say, uniform random noise, you have an image, you sample small uniform random noise within your like L infinity ball or whatnot. You can do this randomly, right? And of course, for a fixed example, if you sample like a lot of different noise patterns and you evaluate the model, then you can either evaluate the average, right? You basically count how often is the model right on average across all these different noise patterns for one fixed example. Or you can do the worst case. You can look at, okay, I have one image, I sample like 1 million different noise patterns, and I select the image, this noise pattern where the model performs the worst, so where the model makes a mistake. right?
Yeah.
Kind of a worst case style of evaluation. And now adversarial examples are in this kind of worst case notion, only that you don't generate like a million different noise patterns, but you optimize, right? You have like a gradient descent optimization that instead of sampling noise patterns and trying that out, basically like a brute force optimization scheme, you just do gradient descent and you end up with the right noise pattern quicker, right? So in a sense, these adversarial examples are like a worst case evaluation scheme. And now if you, and maybe as just as a side note, this doesn't have to be noise, right? You can also say, okay, I want to have rotations of my images, or I want like in audio, I want to have like a pitch shift, right? Or in text, I want to have, I want to have typos or something like that, right? All of this I can generate randomly and then have like this average case of evaluation. But for all of these, I can also devise methods of kind of adversarially perturbing, adversarially changing the examples. And then I'm on the adversarial example side. And there are actually quite a few methods and papers that explored having these types of adversarial examples, sometimes on noise, sometimes on rotations or whatnot, and integrating them into training. And I think this works, but it very much depends on what you're interested in, right? So for example, if you know that you have a specific distribution shift at test time, right? And you maybe don't have a lot of data from this shifted distribution, but you can describe it, right? So let's say you're training an image classifier, and you know that at test time, the images might be flipped, they might be rotated, something like that. Then having this kind of adversarial style rotation data augmentation might probably help your generalization, right? And so it's definitely a kind of a good description, and it's a fluent, right? It's not a black and white decision, right? It's not like average case to worst case. There are like things in between, and you can combine and so on. And I think nowadays it's very widespread. Like data augmentation in general is widespread, but like auto augment, rand augment, and so on, these are to some extent adversarial, right? Because like you optimize, like these policies are optimized for something. They might not be optimized for robustness, but they are optimized to be particularly difficult for the model, like particularly strong regularization and so on. So I think it's like a continuum in between. And a lot of my work was on the very extreme, like we really want to fool the model no matter what. And a lot of reality is, of course, in between.
Yeah. And maybe on this particular tangent, I want to ask a very open-ended question that this is not directly related to the work that you have but one of the examples that you gave it when you started off your research in this particular direction is the idea that if I add noise to a particular image, I still remember that particular I think paper where they have like an image of cat, they add a noise. To us, like as humans, we still see the same image, but it definitely fools the classifier. It classifies as completely like a panda or something. I forgot the exact example. But so, and one thing that you explained over here is like adversarial examples help the deep learning model learn that particular manifold better, because we are creating adversarial examples that still remains on that particular manifold that it is supposed to be learning better. But would you say that these kind of fooling techniques in some ways can still be on another manifold and like can still be like a very foolish example of like a perturbed image? So in a way, because the reason I asked this particular question is like there could be an upper limit, or maybe like an upper limit to the cap of the performance you can achieve using adversarial examples, but it cannot guarantee like a generalized performance, because there could be an image which is like added noise or some kind of perturbation is done, but it is completely on a different fold, but still the concept or like the inherent characteristic of image still remains the same.
Yeah, that's a good question, and that these are kind of a lot of different topics you touched on. I think in general, how I like to think about it is that you have your data distribution. Your data distribution lives in a very high dimensional space, right? Images like on ImageNet, these are like thousands of dimensions. And of course, you as a human, you don't see an image as like an array of numbers, right? That's not how you perceive it. But the neural network does. The neural network sees an image as a number, as an array of numbers, right? So even if there are changes that are not visible to us, that's part of like how we work, how we construct it. Maybe our brain or like kind of we are built is already robust to some extent to these changes, right? But also, for example, if we think about noise that we used to see, right? So if you in the medical domain, we talked about MRI, but also like X-ray scans and CT and so on. You have professionals that are trained on these, and this is not something you grow up in. You don't grow up and running around in the world and seeing X-ray images, right? So you have more or less grown-up people, right? You start studying and then you start med school and you are kind of grown up and your visual system is kind of more or less built to maturity and your kind of brain has developed and so on. And then they need to learn how to interpret these X-ray images, right? And for them, it's also difficult, right? So I know students, and they tell me, yeah, I mean, you get used to kind of seeing more and more the more you kind of look at X-ray images, but then you go to another hospital and they have a different system, and then it suddenly looks way noisier for you because you're not used to it, right? Yeah. So I think to some extent we humans also learn to kind of deal with it. And the X-ray example is just because it's a very concrete example where grown-up humans actually need to actively learn to see through the noise, where for you and me it's probably just like very noisy X-ray images. And I think the same is kind of true for neural networks to some extent. You have your data distribution that you want to train on, and you expect kind of noise at test time or whatnot, and you want to take that into account. And this, of course, changes your data distribution to some extent. So it really depends on how you define your problem. If your problem is clean generalization, then you just train on clean images. Your test set comes from the same distribution, no distribution shift. Your model performs usually very well. And now adversarial examples can be seen as having like a slight distribution shift, right? Or also random noise. And I like to understand it as you have this distribution, and this distribution kind of can be understood as kind of a lower dimensional manifold in your space, right? And as soon as you have noise types or perturbations or concepts even that are not in your data distribution, not in your training set, then they are not on the manifold of this kind of original training set. First, this is a very kind of abstracted concept, right? Because like your manifold is not explicitly defined. For synthetic data, for example, we can define it very explicitly, right? If you have a generative adversarial network or something, we have a low dimensional space that we sample in, and we generate images, right? We know that these images come from a low dimensional space, and we can make changes in the low dimensional space and see how it affects the images. But I mean, for natural images, of course, we'll probably never know this manifold. But what we worked on a bit is essentially trying to figure out, okay, if we assume that there is this manifold, what do adversarial examples do, right? And I think it's very natural to assume, or it's very intuitive that these adversarial examples leave the manifold in some respect, because we add noise that is usually not present in these images. And the stronger the noise, the further we are away in the manifold. And then data augmentation or adversarial training just assumes that, yeah, we take these perturbations as granted and we just include them in our manifold, right? Which might explain a bit this trade-off, because in adversarial example, if you have these, in adversarial training, if you have these adversarial examples and you say, yeah, I just train my model to also correctly classify the adversarial examples, then I make my problem obviously a bit harder because the manifold is suddenly different, right? But in the end, it really comes down to what you define your data distribution to be, what you want to perform on. Well, right. In your case, if you have a different institute, then for some use cases it might be fine to over-index on a specific Philips machine, right? But if you want to deploy it on other hospitals, then it might not be fine. So it's like, I'm not sure if I have answered your question. I think there were a lot of points to go on, so maybe we can go back and forth a bit to clarify.
Yeah, no, definitely. I mean, yeah, I get the idea. I mean, like I said, like it's an open-ended question, and definitely it's no way, like there is no way a consensus on this, that this idea is being solved. But I just wanted to throw it out and maybe get your opinion on that. Is like the idea of learning concepts, but it's very well that the way you put it is like how we perceive images is very different than how computers or any kind of AI models perceive images. So it's definitely, we need to have some kind of other conceptual work that needs needs to be done in order to solve this issue.
Yeah, but I mean, if you think about it, I mean, there are adversarial examples for humans, right? I mean, you can open textbooks in school and there are these illusions, right? I mean, there's this very popular one with the two arrows side by side, which have the same length, but depending on how you turn the arrows, the left one or one of them looks longer, right? So there are these illusions for humans as well. I mean, people like to call them illusions, but in the end, it's just ways to trick the human visual system. The difference is, of course, that these illusions are to some sort not on a pixel level, right? I mean, in adversarial examples, they just perturb pixels. For humans, these illusions are more like on a semantic level, right? You try to trick the humans by exploiting a bias, right? You exploit kind of a bias that humans like to compare things, right? And so if you compare things, then sometimes they look the same or not, but in reality, it's different. So I don't think it's necessarily that we humans can't be fooled. The difference is just that the things that we are fooled by are very different from the things that AI is fooled by.
Right.
And part of the reason, I think, is that AI still work a bit differently. It's probably also, maybe it's a representation problem. Maybe if we wouldn't represent images as arrays, then I'm not saying that then AI would be perfectly safe and robust, but it might yield different adversarial examples, right? So for example, in generative modeling, if you have a generative model of images, for example, right? I mean, nowadays we have great generative AI. You can kind of a latent space that is very low dimensional, right? And I'm pretty sure that if you train an AI on kind of generated images, you can still fool the AI by finding a perturbation in your latent space, but suddenly the perturbation isn't on a pixel level, right? It's on your latent space in a sense. Right? So it's like, I think a lot of things involved. I think we get close to getting very philosophical here, but these are some things that sometimes I like to think about the fact that humans are of course also very fooled by a lot of things, right? AI is just like, it's just so counterintuitive that AI is very good at things that we have difficulties with to some extent, but then very easily fooled by these obvious mistakes that like every child would get right. And it's an interesting dynamic in a sense.
Yeah, I think the power that both humans and AI have is very complementary. Like we are inherently good at few things that AI is not good at. Like you cannot be fooled, but I can easily fool an AI model. Versus it can process huge chunks of data and create some great, like you can be tired and you can make a mistake. Versus AI cannot. So I think it's just learning. And like you said, like I mean, I would think that these philosophical conversations are really important for someone to think along these lines to like as in what can be improved. Like for example, when the attention model came out, a lot of people tried and still are trying on vision transformer models, because if you see, it inherently changes the way how model sees an image, right? Like the way convolution says an image is like a block by block or like a small matrix, versus the attention model tries to compress the image all at once, or maybe at some certain level. So I think, I mean, I'm not saying that vision transformers are replacing CNNs, but it's like a new way of processing information that could be better in few ways, worse in few ways, but it's like worth exploring. So like
no,
these
definitely.
kind of,
I mean, as a side note, vision transformers turned out to be more robust than CNNs or ResNets on maybe not on, I mean, adversarial examples. You can also compute them for vision transformers and they work very well, but adversarial examples are, of course, they might look different for vision transformers, but there are like, you have architectural changes, and of course this kind of impacts like how you kind of generalize to specific distribution shifts, or whether you're robust to specific types of noise, right? If we think back, this was kind of one of the things of one of the motivations of convolutional networks, right? That we have these translation invariant kind of things. There's a lot of work on having more than translation invariance, having like invariance to other transformations. So I definitely agree that there is this component of different architectures and so on, and we've tried out a lot of them. There's of course always this argument, how similar is it to the human visual system and so on. I'm not sure if that should be necessarily the target, but I think it's interesting to see how these things inform, right? Because we humans like to think in attention. So vision transformers, attention models are a very natural way to kind of approach these things. Yeah, it's interesting times.
Yeah. And one of the other drawbacks that I feel AI models definitely do have is the idea of it does not have the dimension to say, I don't know. So inherently, the idea of deep learning model is to maximizing the low confidence, right? So even if it is very low on a particular prediction, it will try to maximize the probability, and that is inherently very, very wrong in terms of like learning the concepts, or maybe like the just idea of on manifold learning. And like you have a follow-up work for this one is something you have like confidence calibrated adversarial training work. So can you tell more about like what was the, I mean, we definitely talk about its intuition, like what is the problem at hand, but what does that particular work do, and what do we mean by making the model learn that okay, I don't know is also a plausible answer in many of the cases?
Yeah, that's a good question. And I think, I mean, we already covered a bit this kind of idea of manifold and adversarial examples, to some extent leaving the manifold. And you can show this very concretely in experiments that if you have a data set and the data set implicitly defines a manifold, then you can show that locally adversarial examples kind of try to leave this manifold in almost an orthogonal direction. So it's very natural to think that, okay, and I also said that adversarial training or data augmentation essentially says that, okay, we want to be robust against these changes. So let's just include them in our learning problem. And we kind of thought, okay, maybe there is kind of not a smarter way, but a different way of doing it, which would be that you acknowledge that some distribution shifts you don't want to necessarily classify correctly, but you want to, as you say, reduce the confidence. You want to indicate that this is something that you shouldn't classify on. This is something that might have been manipulated and so on. And confidence calibrated adversarial training does exactly that in the setting of adversarial robustness, but there are very similar methods, for example, in out-of-distribution generalization, where you can do the same thing. You just train networks on your data set as regular, but then you kind of add out-of-distribution examples, and you force the model to have like a uniform distribution or like a low confidence prediction on these out-of-distribution examples. And we did a very similar, we did something along that lines for adversarial examples. But adversarial examples, the problem is that clean examples and adversarial examples are by construction, by definition, very close together, right? We usually constrain adversarial examples in terms of an LP norm, right? We say L infinity adversarial examples, the difference between the perturbed and the clean image is within an epsilon in terms of your L infinity norm. So this, of course, has some difficulty. So you can't just say, okay, let's force the model to have low confidence on adversarial examples, because this will just like not work very well. This will not be trainable. So what you have to do is you kind of have to guide the network a bit more. And we did this by explicitly saying, okay, on the clean examples, you should just reduce cross entropy loss, just do high confidence predictions. But the further we go away with our adversarial examples, so the larger the distance between the perturbed image and the original image, the more and more we want to converge to a high entropy prediction. So like a uniform softmax prediction, essentially. And there are some kind of challenges here and there on how you do that. For example, the usual methods you use for computing adversarial examples are not really applicable anymore, because they usually operate on maximizing the cross entropy loss. But if you have a uniform or like a low confidence prediction, this is not necessarily the kind of right way to kind of fool the model. And there are some challenges during training. It's usually a bit more computationally expensive. But what is actually very nice in terms of the results is that you overcome the robustness accuracy trade-off to some extent. So the trade-off we talked earlier about, that adversarial training usually results in lower performance on clean examples. You can avoid that to a large extent, which I think to date there are no adversarial training methods that can do that. And I mean, again, this is kind of intuitive, because adversarial training just makes the problem harder by including adversarial examples. And confidence calibrated adversarial training basically says, okay, we still want to do the original problem, and we want to just say, okay, we don't know on everything else. And another benefit is that you generalize a bit more to the type of adversarial example that you encounter. So one problem with adversarial training is that, as with data augmentation, essentially, you are only robust or you only generalize to the augmented examples that you see during training. So if let's say you do data augmentation on rotations, then you might not be robust to like flips or to crops or something like that, right? And the same as with adversarial examples. If you compute adversarial examples a specific way, for example, you constrain them in the L infinity norm, at test time, you're not robust against adversarial examples that are constrained in the L2 norm or against other types of adversarial manipulation. And confidence calibrated adversarial training overcomes that the robustness generalizes a bit better. And this is, of course, the notion of robustness also changes a bit. Adversarial training, the robustness means you correctly classify all adversarial examples. In our case, robustness means you reject, you assign low confidence to adversarial examples, indicating that you don't know, right? So I think there's no right or wrong. I think it's just like a different perspective. And I think nowadays, a lot of people are thinking along these lines because we have these really powerful models. But for decision making, you still have, like, if you want to do classification or something, you still have this inherent problem that, okay, you are interested in specific distributions, but if you allow the user to kind of input anything or something, you want to know when you can trust your model and not. And confidence calibrated adversarial training was kind of a step in that direction from the adversarial robustness perspective.
Yeah. And I would be curious to know, as in, did you in this particular data set where you did the experiments, did you assume that there is no class imbalance? The reason for that is, like, if there is an inherent class imbalance, like without using these kind of techniques, you would obviously assume that the model will be always low confident on the minority class. And in a way, when we use data augmentation, it tries to overfit. So that is like, if you see like the normal training method, if you use just like an oversampling or standard data augmentation techniques, the model will be always overfit on the minority classes. And in this case, like, I mean, this approach would be useful when you have like a very perfectly level of all class labels. But like in cases of where you don't have perfect class balance, this would, like, I mean, I would say it would create like a different design of experiments, but it needs to be updated, right? Like, just, I would like to
know it's a good comment. I think we didn't particularly look at that. I mean, most of the standard data sets that we worked with back then were like balanced by construction. I know, or it is well known, that in general, machine learning, of course, doesn't assign accuracy in a fair way across classes. There are a lot of different perspectives on it, right? I mean, you can see it from the class balance perspective. There's a lot of work on that. You can see it from the fairness perspective and so on. Also for robustness and for adversarial training in particular, it is well known that for some classes, it just works better than for others. Some classes are just more difficult than others, right? And I would assume that the same also holds for confidence calibrated adversarial training. It might be that for some classes, the model learns to be maybe too confident on more difficult classes, or not confident enough on difficult classes. It's definitely an interesting question. I never tried it out. As soon as you have the option to, essentially what you do is you have an option to abstain, right? You have an option to reject examples. So you have, instead of like previously, you can be correct or you can be incorrect, but now you can be correct, you can be incorrect, or you can abstain. Of course, you can you can correctly and incorrectly abstain to some extent. So evaluation gets a bit tricky, but yeah, there are a lot of, like, you could, for example, ask, okay, on which classes do I abstain more or less? Right? And if you now translate that into a fairness world where you don't talk about classes, but you talk about attributes like gender or countries or whatnot, then of course you want to make sure that if you have like a classifier for something, you want to somehow make sure that you don't abstain on one gender and correctly classify the other gender, right? So it's like it's definitely an interesting question, but we didn't look at it in particular, but I'm pretty sure that that would be an interesting experiment to do, given that adversarial training and like deep learning in general has this general problem of treating classes separately, and then if you have class imbalance, of course it gets worse if you have like a long tail and so on.
Yeah, that makes sense. And I think one of the few works that I think you have brief amount of time working on it, but I'll let you describe more is, and to me it's fascinating just even from a surface level, is the idea of using deep learning based accelerators, so deep neural networks accelerators. So can you, like, I mean, I won't give a shot at like what exactly it is, but like to me, like I had a brief time working on binary neural networks, so it was like very fascinating to learn that how just a simple modification can help you with like the improving the memory performance of whatever computational resources you are using, the computation time that is needed, still not sacrificing the performance. And at some point, like when I worked on that, like I just thought, oh, then it goes to show that, okay, there is a lot of redundant computation that is being done. But again, I won't give it away, but can you tell a bit about the idea of using deep learning for creating hardware that is much more specific to deep learning architectures, and what was the work that you worked on?
Yeah, that's a good question. Maybe let me get a step, take a step back and connect it to the general work. So, I mean, by now it might be clear that I spent most of my time working on these uncertainty and robustness related problems. And adversarial robustness, or robustness in general, is usually viewed through the lens of the input space, right? So you have a model. The model have weights and inputs, and it makes a prediction. And you want to be robust to inputs that you haven't encountered before, inputs, concepts that you haven't seen, perturbed inputs, adversarially perturbed inputs, and so on. But there's, of course, the weight dimension, right? The weight dimension. And when I started working in this direction, there was already, for example, a lot of work on quantization, right? I mean, people were curious, okay, we do all this in kind of floating point. This is like expensive. We have millions. Today we have like billions of weights and so on. And yeah, we need to run this somehow. So why don't we just use less bits or less information? And it's worked, of course, surprisingly well. I think a lot of people were surprised. You were surprised that you can get away with like binary quantization and so on. But what is essentially, so this is one perspective, but the other perspective is if you do quantization, you introduce a quantization error, right? You introduce errors on the weights. So you can see, yeah.
Can you also clarify what do we mean by quantization over here?
Yeah, that's a good question. So in this case, quantization really means on the weights, right? So we want to get away of like storing weights in floating point format, and we might want to have binary weights. We want to store weights in as 8-bit integers or something like that. So we want to spend less bits, less memory on the weights. And this, of course, has two components. So I think nowadays the literature mostly converge to kind of, and this is really in the signal processing sense. I'm talking about quantization, right? I have a signal. The signal in this term is the weight, and I want to quantize it into a specific number of bits to fit into my memory or whatnot. Nowadays, so I think the literature started with quantizing weights. You want to have less memory requirements for your weights because we were developing all these big models and they were expensive to store, obviously. But you can spin this further, right? It's not like just about the storage. If you store your weights only 8 bits instead of 32, this also means maybe you can do the computation in 8 bits instead of 32, right? So suddenly you do more like integer style computation in your processor than like expensive floating point and so on. Which means that then you also have to quantize your activations, you have to quantize your gradients and so on. So nowadays, I think it's very standard that if you talk about quantization, usually people assume that the whole, at least at test time, the whole thing is quantized. Your operations are quantized, your activations and your weights and so on. But when I started working on it, I was really mostly focused on the weights. Why? Because quantization of the weights you can see as a robustness problem. Because if you go from a floating point number, let's say like 1.2, and then you want to quantize it into a specific number of bits, 1.2 you might not be able to represent. You can only represent maybe 1 and 2. So you round off the 1.2 to 1. So you incur an error of 0.2. Right. So now the question is, how does the network react to that? Right. Now you do a forward pass after the quantization and you notice, okay, suddenly the accuracy is lower. Right. So you can see it as a robustness problem in the weights. You introduce errors in the weights and then you observe what changes. And this is kind of the angle that I went into it. And now coming to these accelerators, to the hardware, is the goal of deep network or deep learning accelerators is you want to have a very cost and energy efficient ways of running, right? So just for inference, we just want to run neural networks. Because like usually you do it on your GPU, but of course the GPU needs kind of a lot of power, and it might not be necessary just for inference. And the other thing is, of course, like if you think about cars or robots, you just want to have like more energy efficient, smaller hardware and so on. So these deep learning accelerators do exactly that. They basically are custom made for a specific architecture or for a specific problem. They're custom made for specific quantization and so on. And one main purpose is really to be energy efficient. If you want to deploy it in robots or in autonomous cars and so on, you want to be energy efficient. And one way to, and there are limits to it, right? There are physical limits. I had physics A levels, but a lot of that knowledge is gone. But I think on a high level, you have the chip. The chip consists of like your processing units, your memory, and so on, and different levels, kind of a hierarchy of buffers as any regular PC, any regular CPU does, only like in a smaller scale and more optimized. And you can't, and one main influence point for the power consumption is the voltage. And you can't just reduce a voltage forever, because if like your processing units, your memory, they all need like a minimum voltage to work reliably. And the main constraints for a lot of these chips is really the memory. So if you reduce the voltage, so I think power, the energy consumption scales quadratically with voltage. So you really want to reduce voltage because you get a quadratic advantage. And the first bottleneck you hit is memory. Processing units usually don't require that high of a voltage, but memory often does. Depends on the type of memory and so on. But you scale down voltage, and for some memory types, what happens is that if you reduce voltage, at some point the memory becomes faulty, right? So reading and writing kind of your bits becomes unreliable. So in the easiest case, right, for inference, I have my weights stored on the memory. So now I reduce my voltage, and now I want to read these weights to do an operation, right? So when I read these weights, I have errors because the memory is not reliable. So sometimes I read a 0 where I really should have read a 1, and the other way around. And this also introduces errors, right? So on top of the quantization errors, we now have these bit errors essentially. And this is something that we studied together. This was a collaboration with IBM Research. This was a postdoc that I met at a summer school. And I had a talk there on confidence calibrated adversarial training. And we met, and she said, hey, this could really be relevant for what we are trying to do. And this is how it started. And it's an interesting project, definitely, because it has very tangible impact. And the problem was really, how can you train neural networks that are kind of robust to not only the quantization, but also to kind of these bit errors in the quantized weights. And it's for me, it was really an exciting project because, I mean, you learned about binary networks and I also had to learn about quantization. It's very different. I think there is a lot of literature on it, but it's kind of in the intersection of hardware, of high performance computing and machine learning. So there are different conferences that you read about, different people that you interact with. Nowadays, there's, for example, MLSys, which is an ML systems conference, right? Where you have a lot of these works that are kind of in this intersection of this. So I found a really interesting project to work on, and it kind of relates, right? I mean, as I said, in retrospective, you can always frame it that it fits your PhD, but it's really, I mean, I really like to view it as a robustness problem. And that's how we kind of worked on it. Only that at the end, what you can do, and unfortunately, I never really worked with the actual chips, but we had data from actual accelerators, and you can really show that, we can now get the same accuracy, but at much lower voltage, and we would save like 20, 30% energy, right? Which is a very tangible thing. So that was a cool project.
And like tying this back to the idea of like there is no free lunch, right? Like there's a very popular theorem. Like, do you think like when we use these kind of techniques where we are trying to cut down on like optimize heavily on computation and memory resources, are we in any ways sacrificing the performance? Or maybe the test set is limited, right? Like you hold out a test set where you are performing all of these experiments. But let's say when you apply this model into the real world, would you guarantee that this model would have learned? Because we are intentionally introducing some of these errors, right? Like in this case, like not in the bit errors, but at least in the case of binary neural networks or something approaches that are similar, we are intentionally making some error so that the model is like trying not to learn. So would you say that in any ways this impedes the training of the deep learning model?
That's a very good question. I think in generally, so I think to some extent I don't know. Because the problem is you might, like, even if like you have a network and it gets like 96% accuracy and now you quantize it, you still get 96% accuracy.
Yeah.
So either you have a free lunch or you're just not evaluating the thing where you trade off, right?
Yeah.
But I mean, if let's say you still get your accuracy of 96%, but on some other data set that you don't care about, it's slightly worse, right? Yeah. This could still be a free lunch. Like, as long as you don't care about the data set and it's not relevant for the application, you solved your task of having a smaller network and getting the same accuracy, right? So that's one perspective. So I think there are probably trade-offs. You might just not be aware of them, and they might not be relevant to the problem at hand. Yeah. That's one perspective. The other perspective is that I think a part of, we have to realize that these models are still heavily over-parameterized. Or like, okay, we don't know how heavily over-parameterized they are, especially depending on what data sets we train on, right? We have lots of parameters. And we also know that, like, if we train them using SGD, we usually end up in very similar regions, right? We use a lot of regularizations to have small weights and so on, right? So it's very likely that a lot of the weight space we never really try out.
Yeah.
Right? So it might also just be that with quantization, right? I mean, we can train with quantization, and it might just be that quantization, it adds a constraint on your weight space, right? It reduces your hypothesis space, right?
Yeah.
But it might still be that the hypothesis space is large enough. We might find different solutions, but it doesn't necessarily tell us that there might be a trade-off, right?
Yeah.
So I think there are kind of different perspectives, and I think to really kind of say, like, definitely there's always a trade-off, right? There's no free lunch, or there's like we always kind of pay a cost. Yeah, we might also have to evaluate like every possible dimension, and we are not doing that, and it's also not relevant for a lot of tasks. And yeah, maybe we are also just lucky in that we have like all these parameters, and like the regularization, the data augmentation, the network architecture, all of that already constrains the hypothesis space. So maybe using quantization on top, that also constrains the hypothesis space. But maybe like in this hypothesis space, there's still kind of a lot of good solutions. Only that without quantization, we find different solutions, and with quantization, we find like slightly other solutions, essentially. I'm not sure. What do you think? I mean, you played around with binary networks. What's your take? Did you get the same results?
Yeah, we did get. Yeah. I think there was a decrease of, I think, 0.01%, but I think the like we did that trade-off where we said that, oh, we optimize. I think there was a decrease of I forgot the I think it was something around the percentage of 30s. So like there was a decrease in 30% in computation time. We used the same resources, so there was no way of, but we used a higher batch size because we were able to load in more data because we were trying to decrease the model size. Yeah. So that was the idea in that one. But like but I agree with that one, because at some point I would say, I would try to retract that question, is like, I wouldn't say that there is no free lunch, but I would think there is like kind of redundancy that what we might be doing right now. Because I'll give you one example for the same project that I just mentioned earlier for the brain age model, right? So we have like 3D images of 7,000. So we have 7,000 3D images. That's like a huge data chunk. It's like around 200 gigabytes of data that I'm trying to use when I'm using ResNet 18 model. And this was like this was not even my purpose to introduce something like quantization or bit errors, but it used to take me 4 days to train one model for like 80 epochs. Yeah. And like 80 number, like even I figured out after, like I knew that this was like the kind of the stable curve where it is not overfitting. And so whenever I would go back to my advisor, she would say, oh, do this, like, let's try this. And I had to wait for 4 days. So that used to irritate me, right? Like if I did something wrong, it will be only. So that's when I think when I learned about the floating point precision that PyTorch has, right? So 16, 32, 64, and the by default one I think uses 32, I think. So that is the time, like one of my lab mates said, like you should just try with 16 because that will just help you, and you can actually fit in much more batch size, because I was limited. I mean, I was using 800, so I was lucky that my lab has 880 gigabytes. But even with that one, so completely, I was able to replicate all the results as it is, all the trends, like the bias trends that I was trying to work on and mitigate. I was able to replicate everything, and that, like I was able to do that in less than, like, I think 1.5 days or something. It was similar to that, and I was like, wow, like was I doing anything redundant? So it's not exactly free lunch, but it's like if I started with 8-bit or 16-bit precision, anything above that is like just unnecessary computation. So it would be like basically your work that you did over here is like just maybe trying to have a threshold above which you can say, oh, this was all redundant. It's not like free lunch, but it's like extra lunch. Like you don't want to eat extra than what you're hungry for. So it's something like that.
That's a great story. And I can feel that. I mean, I think, in a lot of cases, there are also like real world constraints that in your case, for example, I mean, you could still train it in 4 days, right? But I mean, there might be like researchers out there or models out there that you like, if you train it without quantization or something, you might never really converge properly. You might not be able to do the same number of epochs, right? You might not be able to fit the batch size into RAM and so on, right? So I think in a lot of sense, and that's why I'm not sure if there's a free lunch, right? But I think it's just like we have limited we have limited capacity to do experiments, both in terms of time and in terms of resources and so on. So there might be a trade-off, but we might just not be aware of it. We might just not observe it, because the ideal thing of like training everything on all the data for as long as it needs on full floating point precision, that might, in a lot of cases, that's just not an achievable goal. So you don't know which number you would get. Maybe you would get 1% more, but you never observe it, right? So I think there are kind of a lot of things to that. But yeah, I agree. My experience was too that like above 8 or definitely above 16 bits, it's usually, it really doesn't make a difference anymore, and it kind of speeds up your computation quite a bit. On the other hand, of course, it's a time thing, right? I mean, when deep learning started, like, you need to have this technology available, right? Because for you, like if you would have to do like 2 research projects simply to get like binary networks working, this would have been a different story. But in your case, it seemed like you could just use like existing technology and try it out, and it helped immensely. And that's great, right? I mean, it's great that people worked on that a couple of years ago, and you can just use it.
Yeah. And I think personally for me, this field is like very exciting for me, at least, like even if it is nothing a part of my PhD, because at the end, before I started my PhD, I still call myself as an engineer. And like the idea of just optimizing things, optimizing it for the sake of resources or time limits is something like I just get fascinated. Like even till date, like on weekends, I tend to work on my existing code and just make it efficient. Just make it like, it's like using arguments. Like it could be just like very silly things, but if I want to replicate these results, so that like if anybody were to step into my shoes and just use my code, they can just use it. So like just making it more efficient in terms of implementing the code, and also like running it on hardware is just something fascinating for me. Like I just try to learn more and more about it.
No, I agree. It's a nice topic. And I mean, in academia, there are usually the incentive to do, you don't have a direct incentive to do it, right? That's kind of the problem. You don't have a direct incentive to have nice code and to like have it run efficiently and to optimize for your hardware. But I mean, in the end, if you can run the same experiments and you can iterate in half of the time, that's like a very tangible effect on your PhD, right? You like either you do more projects or you can like run more experiments. So that's, for me, this was always a big factor, right? If I can spend like a week or 2 optimizing something, and I also enjoy doing it. So for me, it was kind of a win-win, and I can run experiments quicker, right? That's always nice to have. And again, I think it's very, very fortunate that we have a lot of these tools Like it still takes time to implement everything, of course, but like a lot of the tools, if you would think about having to implement quantization yourself and like all the CUDA stuff yourself, you probably wouldn't. But now it's like you can read it up, and in a week or two, you can just like half your time of iterations, and that's great, I think.
Yeah. And I want to switch gears and maybe learn more about you apart from even just your research works, because I think there is a fantastic amount of work that you have done, even outside of your PhD or research related. And I want to start with something that also excites me to learn more about is like you're working at DeepMind, one of the coolest labs, like as a researcher, like when you are in your PhD, like it's like places like this that you want to be working at, because it feels like there is a great amount of great research being done, impactful projects, and great team sets. So in your terms, like when you join DeepMind from academia, what do you think are the most amazing aspects that you feel working at DeepMind is? And I know this is like a personal opinion, it could be just specific to you. What excites you most working at DeepMind?
Yeah, that's a good question. I mean, I think there are a lot of different aspects, and as you said, it might be very subjective and very personal kind of decision and view on things. I think a couple of things that many people might agree with or might agree on is, so first, I think there's just like an incredible amount of talent in general. And this, of course, is on the research side, right? So if you want to do a PhD, you of course select your PhD by like who you want to work with, what you want to work on, like what does the institute do? Is there kind of a lot of resources? Do you have like famous researchers from there? Do you have like to get people prizes and so on, right? A lot of things you look at. And at DeepMind, you have a lot of that. You have a lot of smart people, not only at one organization, but to a large extent also in one city, right? In one office, essentially. And this makes a lot of difference, in my opinion. And with COVID, of course, there's a lot of discussion about remote work and so on. And but it makes a difference because, like, a lot of the conversations you have, kind of during lunch, during events, you have with people that are very accomplished in machine learning, computer vision, NLP, and so on. And this, of course, has a lot of benefits. I mean, you have cool projects, you have cool collaborations, we're always on the edge of time. But for me personally, it also means that there's so many people that know more than me and have more experience than me, and that I can learn from in various ways. And this doesn't only apply. So I'm of course talking a lot about the research, because the research is what you publicly see from DeepMind. But I mean, the same is true for engineering we do at DeepMind, or kind of Alphabet in general, and also beyond that, right? I mean, organizational kind of program management, product management, and so on. There are just a lot of smart people and a lot of people that are very experienced in these things that you can learn things from. And I think for me, this was, I think, the key thing. And of course, I had the advantage of having done an internship, so I kind of knew some of the people that I would be working with. And when it came to the decision, I thought, yeah, I mean, are these people that you want to work with for a couple of years? Are these people that you can learn from? And definitely, right? I mean, not only because they're smart and accomplished and so on in my field, but some people I work with also have very different background, right? Come from different disciplines or have worked very extensively on specific topics that I don't know a lot about. And so for me, it was kind of a great opportunity to just like join an organization that had just like a lot of opportunity to learn and grow, basically during every lunch, basically during kind of in every project. And of course, like day-to-day work is, you have your project and you can't just like work at the same time with everyone and learn from everyone. But it's still nice, you know, and there's kind of a lot of talks going on, and of course to some extent it also attracts external kind of talks coming in and so on. So I think that was for me the key factor. Besides that, and this also goes a bit into industry versus academia in general, but for me, I like the engineering part. I mean, we just talked about, right? I mean, I know a lot of PhD students, and this is really not meant in a negative or positive way, right? It depends on during your day, what do you like working on? And there are people, and I would count myself, and from what you said, I would count yourself as that enjoy the engineering part, right? That like to spend time on like having nice code and optimizing a bit and running a bit faster. And as well, there are people that prefer to do the writing or the presentation, and that are not too keen about learning about the next quantization scheme and the new GPUs and how I can run it on the next cluster and so on. But I always like the engineering part, and there's of course great engineering talent at DeepMind too, and a lot of great tools, and DeepMind values engineering to a large extent, and I like that. I think the engineering is valued a bit more than, or significantly more, in my opinion, than in academia, and it's one of my strengths. So it was very natural to this was a kind of a very good additional point. And then another part is also that I knew that but this might also be kind of this might also be due to kind of the stage of career you, like in a PhD, you usually work on your own projects. And then of course, as a postdoc, as a professor and so on, you have bigger and bigger projects, you have more and more collaborators. But I felt DeepMind has a nice organizational structure where it facilitates working in bigger teams. I would like to, this was a contrast to my PhD, where kind of a lot of projects were driven by me and were kind of individual projects and so on. And I wanted to try that out. I really was curious to work more in larger teams on like bigger projects, and longer term research problems and so on. So I think these were a couple of the key things for me, really. But again, we talked about like coincidence before. I was also lucky that the people I worked with during my internship, we got along very well. We are kind of on the same page, and I think that's kind of a main or like a significant factor as well, right? That I like the culture, I like the team, and so on. So these are of course very subjective, right? I mean, people I get along with, that doesn't mean that you get along with them, but personally for me, of course, that's a big factor.
Yeah, and I think the more you are in your research, the mental rigor of your teammates matter a lot. So I think in research, I've seen like it's the idea of thought process is very contagious. If you have a set of people who are approaching a particular problem in a certain kind of way, that's very addictive. And if you find the perfect set, like it motivates you, because as a solo researcher, like I don't know, like unless you are like a brilliant person like Einstein. I don't know if Einstein worked solo or not, but I think most of the people that I would know have come up with thoughts or works that has been really, really critical, and who have always worked in groups, because like a fantastic idea cannot be just a creation of one solo. So I think, and when you're working on, and I would assume like DeepMind just doesn't work on just one very narrow topic. They have like a very bigger impact. They're trying to work on something that's applicable to not just computer science domain or AI domain. They are applying it on real world, and that just begets the problem that, okay, I need to be much more inclusive of thoughts and inclusive of expertise. And I think that's why I think having people who align with you on a mental level is really important, and especially in a research lab.
Yeah, definitely. I mean, I agree. It's like, it's also learning different ways of thought, of thinking, right? Different ways of developing ideas and so on. Do you mostly work on like in your PhD the projects? Do you usually have a lot of collaborations with PhD students in your lab and stuff, or?
Yeah, I think I have been fortunate enough to actually, like, I would say I have the least amount of people I have interaction are computer science students, because my professor who funds my research, essentially, she's from industrial engineering background. So, I mean, she had her background in mechanical, then she did her PhD in industrial. And nowadays, I think since the last 10 years or so, she has been heavily invested in medical AI. And so obviously a lot of people in my lab, they are from data science disciplines, industrial engineering, and there are just a couple of computer science students. And I frequently communicate with people from medical background. So these are like MDs or people who are like experts in medicine. They just understand AI for the sake of like, it works. It does classification. It gives you F1 score, prediction score, accuracy, and all those kind of stuff, but they don't understand the working behind it. So I think it's like a constant juggle. And what I feel very very useful for me is like, because I have to summarize my work in 3 different genres. So when I'm working with my friend who's like a computer science student, I have to talk to him in a certain way that, yeah, this is the nitty-gritty details of what's going on under the model. No BS about it. But then when I'm summarizing these things to my professor, who necessarily doesn't know how exactly data augmentation works, but she knows most of the stuff so that she can critique. And then when I'm communicating this to a doctor, he or she doesn't really care about what model I use. He doesn't care what ResNet 18 means and what ResNet 52 means. He just knows that it's a black box. What do I do with it? So it's like this frequent, like changing the hats into different topics really helps me motivate and like maybe get some new ideas that, yeah, if like don't get stuck up on data augmentation too much, like the problem is much more bigger at hand, or something like that along those lines. So yeah, I mean,
yeah, that sounds great. I mean, I think it can be challenging, so I get that point, but I think so it might be, it's not something you optimize short term, but I think it's a very valuable skill to learn, that you like find the right level of abstraction, the right way to phrase it, depending on who you talk to. And yeah, I mean, just like mirroring that to in the collaboration with IBM Research, for example, that was the same, right? I mean, there was somebody sitting there, probably with an electrical engineer background, telling me about like how static memory works and like what's the voltage, and I was sitting there trying to explain. And it really took a while to kind of find the right vocabulary and the right kind of language. But it was very rewarding once you were on the same page and you could actually work. So yeah, sounds like you have like a really interesting setup.
Yeah. And I think, like you said, like it brought, even for in your case with IBM, like it helps you figure out a problem that has like a real impact, and it also helps you with your thesis, right? Like you said, like you connected it somewhere back to robustness. So I don't know if it helped or not, but like in some cases it might also help you induce better thoughts when you're working with robustness. Like you might be stuck up on some problem, and it gives you a different perspective that, okay, what if I consider this problem like this, and it helps me solve a problem. Oh, but you also go back to your original thesis and saying, oh, why don't I just borrow this idea into my this particular approach? So it's very translational. Like the idea of getting the meta insights from research is very translational. You can take from one thing to the other one.
Definitely. And maybe tying it back to DeepMind, I just feel it takes commitment and it takes time to build relationships or to interact with people that have different thought processes or come from different backgrounds. But I think every time you do it and you invest the effort, it's like you have basically one more way of thinking in your kind of tool belt. And that's one thing where I think like just having a lot of smart people from different backgrounds is like a valuable thing. You can't learn like from all of them at the same time, and it's challenging. It's more friction at sometimes, but it's like if you do it step by step and you kind of invest time, I really enjoy kind of learning about these different ways of thinking and different approaches to research and so on. So yeah, for me this was always a try. I can always recommend making decisions at least partly based on the people or the researchers in a sense you are going to work with.